Okay, let's focus on Rust now. All right. So this is where we were the last time. We are a fully working example of our Welch algorithm in Rust. We even have be able to compute the power spectrum density. It's not that of our signal, showing that we kind of implemented the algorithm correctly. So now we're going to see how we can improve a bit our code, like in Rust. So yeah, we have two options here. I was also thinking that we could add also noise to the signal, and we can see how to add noise to Rust. Or we can go directly try to improve our Rust algorithms and library, making it a bit more friendly from a user perspective, which will force us to dive into a bit more details of the programming language itself. So what would be your preference if I have to ask for a poll here? Could we dive a bit more into the Rust language itself, or look at the noise aspect?
I would prefer the second option, because if we do that after including the noise, the example would be more complex, and for now it's not so complex, so we can focus more. I don't know if it makes sense or not.
So you say the second option for you is which one, sorry?
Yes, to dive deeper in the language and try to make it more, I think that you said, more easier to read or to improve the code.
Okay, if everybody agrees, let's do that. Okay.
So if I wrote a program and then I wanted to share it with other people, would I try to create an executable, or what would be a good way to do that?
Okay. I will have to explain that. I try to remember, because I did that. You can create an executable, and with Brian, I think you did that, and you can be able to use at some point cargo install, right?
That's
so
right.
There's something called cargo install. Honestly, I don't remember the detail. I will have to look at, but I remember that you can ask some if you want to create something that an executable that you want somebody to use. An easy way is to ask this person to install Rust, because it's straightforward, and then one version install in command line. We can use cargo install, and they can specify. You see, they can specify a Git repository, for example. So if you commit your Rust little project application to GitHub, you can give them the URL and ask them to install the library with cargo install --git and the URL, and that's the way to go. Do you have to do something on your side for it to work? I don't think so. If it's a binary, if you don't make a library but a binary project, I think just like that will work.
Okay. Yeah, I was wondering if I wrote something and then I wanted to run it on a different machine, like one of the Amazon machines, for example, how I would actually go about doing that. But I think that is the answer.
Yes, that's one way to do it. If you're not going to make any change on the machine you don't need to clone the repository, you just need to install like a regular. That would work.
Mm-hmm.
Okay. Maybe some details I forgot about, but I remember I did that some time ago. but it's a good avenue to explore.
I
Okay.
think you have an example of how to install it on the M1 thermal model that you generated.
Repository M1. Which one would be M1? Maybe this one?
Maybe.
This one.
Yeah.
Oh, yes,
think
it
it's
is.
that.
It is. Okay. I will send that to. I'll put that in the chat. Here I was explaining the user how to do it. So I think that will give you, if you follow this example, you should be able to do it. So what I was saying to the user, first install Rust. So following the link like this is what people have to do. And then cargo install like that. And then that's all. And in that case, they also have to have some data that I ask them to download and where to put them. And after that, people can use it. And the name of, so that creates an executable on the host machine. And the name of the executable to run is the name of the crate. So in that case, here it's GMT M1 thermal influence functions.
And
So
this example is interesting because you just share one time what you need to do, and the user, every time that he installs, he would get the latest version.
Yeah.
So it's you don't need to share the source code. It just
exactly.
takes it from
That's
the
very nice.
repository.
That's very nice. And you just cargo install the Git repository, the branch, in that case, and people should be able to use it. It's very portable that way. That's pretty neat. Okay. And then yeah, I think you have your answer here, Christophe. That's the way to do it. Okay, let's go back to our example, to the code itself. Okay. So let's see. Let's see where first our code could be improved. So we have our signal that we pass here. Okay, but what if later on we want to compute the sum square of the signal, for example, that we can do, for example, signal dot iter dot map. We take the square of each element and we sum them like that. We're all familiar with iterator now, so that's good. So that's the way to take the sum square. We iterate through the signal, we square each element, and we sum them. If I do that, let's try to compile that with an example like this and see what we get in cargo. Cargo. Build. Cargo. Build. Example. Wedge. Okay, so this is our method I was hoping. Maybe it doesn't work. There's some warning, but we don't care about the warning. It's really that part here. Maybe I can a little before, a little bigger. Voilà. So here it says a value borrowed here after move, and the value is moved here. So it's a very common, when you start coding in Rust, very common error that you're saying. And so that's going to help us to introduce the concept of borrowing and ownership in Rust, which is different from other languages. So it says the value has been moved here. That's the reason why we cannot use it here. When the value is moved, you cannot access it anymore. And it's moved because if we go back to the library, you see we copy a vector here. We could, if we were using a reference, then that could help us if we are passing a reference. I want to spend a bit of time on going, now that we have a working example, I want to spend a bit of time playing with Rust, what I call Rust fundamental. borrowing, ownership, all this kind of thing. So, but let's start from the very beginning, very beginning. Something that you have noticed, maybe, let's see. If I do let A equal 1, and yes, and now I do A equal 2, oh, what did I do? I erased that word. No, A equal 2, sorry. Voilà. Let's see. Error. Cannot assign twice to immutable variable. So I did that on purpose because there's also a concept that we need to be aware in Rust, which is different from the borrowing and so on, but I wanted to go back to the fundamental a little bit. Every variable in Rust, per default, is immutable. So when you assign a value, you cannot change it. Unless you have to be explicit. If you do that, it compiles. That works. But per default, it is not. That's fair. I've been introduced to this concept of variable mutability several years ago, and at first I was a bit shocked. I mean, how come you make variable that you cannot ever change? It doesn't make sense. But you would need that. I mean, that doesn't make any sense at all to me at the beginning. And then I start to read more about it. Why people would even try to program like this. It took me a while to get my mind around it. But now that I understand a bit more why, I came around. And now I even wonder why we write code where we can change variable. Why do we want mutable variable? We can even have, and the reason why is when you have a variable which is immutable, and you need to apply modification to this variable, there's a few programming languages which have only immutable variable, and the way around it is to apply function to this function, to this variable. So if you want to modify it, you feed it to a function, and the function creates a new variable. So you don't never modify it. It's why this method, this way of programming is called functional programming, because you can only operate on the data through creating function and applying transformation to your variable and write the result to a new variable. That seems weird, but that means that you always know in your program what a variable is and contains. It never changes. And when you have a very large code base, a very large code application, it saves you a lot of programming error. And when you throw into the mix pointer and references and so on, you avoid a large slew of error. It's a bit more difficult to conceptualize and to program because we're not familiar, but it's because we have been badly educated, because we have been educated with mutable variable and we used to play with that. But immutable variables are very powerful ideas that really can simplify a lot of things. But it's a very different way of programming. So Rust, per default, its variables are immutable. To encourage us to use this feature and this way of programming, and that's why they introduced iterator, for example. Iterators are really transforming data without really writing to it. In fact, you can write it to it because they are flexible enough, but originally they can't. So that's something I wanted to mention, the difference between immutability and mutability of variable. That's one thing. Okay, so now the concept of borrowing. Let's say let A equal 1 again. And we're going to make mutable. Okay. So that allows me to have B equal A. Okay, that would work.
You should define B, right? With a let.
Yeah, you're right. That's why it's not open. Yes. Let B equal A. And B doesn't need to be mutable. B is immutable. Why not? Yeah, why it doesn't want to compile? Just warning, so that's fine. And now what happens if I move the assignment to B here? You see there's an error. A is not found in this scope. So a scope in Rust is defined with a scope can be as simple as a pair of braces like this, or a function also have its own scope, right? So if you define a variable within a scope, it only can be used when you go out of that scope. The memory associated to the variable is deallocated, and you cannot use it anymore. That's why the compiler is able to track when a scope ends and starts, and when a variable then gets dropped or not. Then that's why it will throw an error, right? So now, if we do something a bit differently, we go back to that. So that the scope is empty, that would work, but now I do T equal A and B equal T. No, B equal A again, like this. Yep. Let again. I forgot the let, sorry, let. Ah, yes. In that particular there it works. Now let's make it because there's some quirkiness in Rust. Okay, it should fail here, if I'm right, if I understand Rust correctly. Yes, we have. So I will explain why it didn't fail as expected. Here it failed. From the borrowing rules of Rust, it makes sense. So what happened here? We create a variable in the main scope of the function, and we assign it to C within a new scope, right? So here A is moved into the scope here. And then when the scope ends, A is no longer in the main scope. A has been moved in this scope, and then we try to reuse afterwards, so you can't. So that's why our functions, that's why in our example with the signal, which was moved to Welsh, when we try to read it after, it's no longer accessible. That makes sense?
So if you wanted to, thinking in like Python terms, sorry, that's just what I have to do. Basically, you're assigning it A, and so when you do let C equals A, it's not creating a copy of A, right? It's like pointing directly to A. And so
it's not even a pointer. It's really, yes, if you want, it's pointing to A, yes. But it's like A, when you assign A to C, A kind of disappear and become C.
Okay, that's the point. So A disappears, it becomes C, and so later on when you're saying B equals A doesn't exist anymore. You have to say, okay.
Yeah.
But outside of the outside of the let C equals A, can you use C? Because C is in its own scope, right?
So C is dropped here at line 6.
Yes.
Because so you cannot use C afterwards.
So everything has disappeared pretty much.
Yes. You don't have access to A or C anymore. So it seems very constraining, but it makes things very predictable. That's what we can say. And so predictable that the compiler will tell you in advance that something, you cannot do that, something will be wrong, right?
If you remove the inner curly brackets, will it run or still not?
That? So let me, that?
Mm-hmm.
Let's see. Nope, because C has been moved to A. So A has been moved to C.
Okay, so
You see, it's a concept of ownership. C owns A now. So that even doesn't, a good question, Christoph. So that doesn't work either.
Rod, when you're making the example, at first we had, you assigned it to A1, and then you changed the type to a vector. What's the difference when you did that?
You see, here it's working. And if you put a vector, it doesn't work. So that is hard to explain. Okay, let me go back to the vector. Example, and I will show you. I think I can illustrate better why. So here it doesn't work. But if you want to have A, C, and B, sorry, A and C both available, no, sorry, to be able to reuse A afterwards, when I use 1 here, I can reuse A afterwards. But with vector, I can't reuse A because it has been moved to C. For a vector to work, you will have to do clone A. You create a clone of A, then A is again available here. So there's no error, right?
So
for scalars, yes, go ahead.
Sorry, A dot clone is like NP dot deep copy, right? Like
yes.
It's creating. Okay. Thank you.
It is. So so not every thing in Rust have a clone method. Vector have, but if you can your own structure, you will have to explicitly define it yourself to be able to do that. Because for a structure, it doesn't exactly know what is inside. For a vector, it knows. For a scalar, scalar per default have I could say they have an automatic clone. Cloning. So scalar are cloned automatically. It's not really a good definition, honestly. But in fact, in Rust, there's a difference between clone and copy. And scalar have a copy property that when you assign a scalar to another variable, it will copy it by default. But it won't do that for anything else. So, scalar is the expression.
Then what's the difference between clone and copy?
I don't remember. That's a good question. That's a hard question to answer. We start to go deeper. Let's see if I can find somewhere where I can explain what's clone, copy. Copy and clone. What did they say about that? Okay. Yeah, here they say copy is implicit and clone is explicit. So in Rust, you have some method that can be invoked kind of automatically, whereas some cannot. So copy is disabled on almost anything, but scalar, whereas clone is available for many Rust collection like vectors or hash map or something like that.
So it seems that when you use Scalar, it's being a copy, and copy is not available for vectors, so we need to make a clone.
Exactly. Yeah.
Okay.
Yeah.
Good.
It's a more difficult concept. Yes, exactly. So that's you could. So But if you need to, you could define a copy implementation for your own vector, if you define your own vector, for example. But per default, there's none. Because you can have a lot, if you have a big vector, you don't want per default to manipulate this thing and create copies all around, like Python do, for example. Rust is much more cautious about memory. Sorry, Christophe?
Oh, so with a scalar, it's always a copy, right? So whenever you, okay.
It's always a copy. Make your life a bit easier. But for a vector, you need to be explicit and call the clone if you need to. So that's for the borrowing and concept in Rust. So you have to clone, a scalar you can copy, so it's a bit simpler. And you have the notion of scope, which is in braces or in the functions where if you move a variable to here inside the scope, if you define a variable inside the scope like that, it won't be usable outside the scope. So now we're going to look at the references. If we define, if we do that, what's going to happen to the compiler? So we pass now a reference of A, of a reference of A to C, and then we assign A to B. Is that going to work? Yeah, only warning. That we can. That won't work because here the value is moved to A. Here it's moved, not copied. Let's see. A vector. Let's go to vector because the notion of copy messed up a bit my explanation. For a vector, you can pass a reference, and that won't work because there's no copy or clone here, so you can pass. And A becomes still available at the end because C as a reference to that. There's no error. Yeah. Okay.
I think, correct me if I'm wrong, but this example is very important for what we do in, what in general we do in IAM. We deal with huge matrices.
Yes.
And I remember the first time that I was making the code with the active optics, and I was loading the interaction matrices, which was big, and I was making some computations, and I had this kind of problem that I was trying to use some data that was used before.
Mm-hmm.
And in order to solve that, I think that I cloned it. And
yes,
it's much better using reference than
if you can use reference, it's better. Yes.
Am I correct?
Yes, absolutely.
Okay. Absolutely. Now it makes sense. At that point, I just used the solution that I got first.
Yeah. So let's play with the reference a little bit to understand how that works. So we do after that. And we do C equal vec 2. That won't work because C is immutable. It's an immutable reference. Sorry, I forgot to put it here. Because C, you see, C has a type of a pointer, and we'll assign a value here. Let me think a minute.
If you make C mutable, it still wouldn't work, right?
It won't work because it expects still a reference. You cannot, once a variable is a reference, it's typed as a reference, even, and here an immutable reference. Mm-hmm. So we can't do that. Okay. Something I wanted to explain. Let me see the best way to to go through that. Something you could do in, something you could do in, something you can do in C or C++, for example, that you can't. You can do that. Let's make everything mutable. Name it. Let C equal C. Or we can let mut C equal A equal A mut A. And if I do C equal vec vector 2, and we look at what is in A. Let's see. Oh yes, just we can define directly. I think we can take a reference directly like that. That would that works, yes. And A has not changed. You see, A is still 1. Because I reassign C. If I do C equal to 0 equal to no, A is 2. You see, because when I do A mut a new vector, I really replace the memory content of C with a new location. Here I index into C, which index into A. Okay.
So no matter if you write on A or C, you are writing at the same place.
Yes. Okay. Because everything is mutable like that. But you need to be very explicit about defining your mutable type. Okay, that's one thing. So, but to go back to our example with signal and passing by a reference, there's something I wanted to illustrate. Let me see the best way to illustrate that. So if I do let A equal vec of 1, oh yeah, and as we see, if I put let's C, even if let's put everything mutable like this, we don't have any constraint. Let mut C, like I did before, equal a mutable reference to A. Okay, here I can still access A because we just pass the reference, right? It's only when I pass the value that it becomes. Okay.
Rod, why, when you say let mu C equals reference, why do you have to put mut A? Why can't you just put A?
You can do that. Yes, you can do that. But then you cannot modify. You cannot modify.
Yeah, if you do this, you probably can't modify A through the reference.
Yes, I think it's that's compiled, but if I do A of 0 equal 1, no, C of 0 equal 1 equal 2 here, then I do that. Because C is mutable. Yes, you see, here it fell because here the compiler is conflicted because I define A as mutable, but I pass it an immutable reference. So I say,
Got it.
hey man, decide what you want to do. Is it mutable or immutable? So that's why the compiler is quite powerful here. You say you define a mutable reference, but you give me an immutable pointer to it. You need to be very explicit. If I do that, that works.
When you do the C and the square brackets, since C is a reference, does it automatically convert it to a vector? Like dereference it? Because C doesn't have any fields, right? It's just a reference.
Yes. I think it's automatically dereferenced. Yes, you're right.
Oh, okay.
Yes.
And then when it dereferences it, or maybe it just can't. I mean, I guess then it gets A, but it's not mutable, or it is mutable.
It is mutable in that case. Yes.
Yes.
So C really become like A now, and it exists like that. Something you cannot do also in Rust is if you do that and you explicitly deallocate A. So how can I do that? To explicitly deallocate A, you can do drop A. I think it's a way to do it. Let's see if it works. Yes, that's a very important point. Yeah, I wanted to get to. So this kind of thing where you allocate a vector, pass a reference to another variable, deallocate it, and then try to allocate a value to the pointer to effect, but you remove from memory the reference you were pointing to. In C, the compiler won't complain. It will allow you to do that, and you will have very weird behavior of your code, and you will be scratching your brain for some time, like, where did something wrong? The compiler tell you immediately here that you can't if you deallocate a variable that you pass a pointer to, then you cannot. Then it doesn't make sense to try to affect a value here to C, because C is just a pointer to A, and A doesn't exist anymore. Something that C and C++ will allow you to do. Okay? That makes sense? Kind of? I wanted to spend some time a bit with that, because now we can go back to our example and see how we can modify it. So here what we want to do is pass a vector here to a library, and then a signal that we are affecting here to the component. We're going to say, okay, it's a vector too. So now we can try to cargo build the library. And here is the expected name lifetime parameter. What the heck is that thing now? So you see how, with little example we have, our Rust as a compiler is very peculiar and very mindful of making sure that if you take a reference and assign it somewhere, you never drop it before you still ask for that value, otherwise it's going to have an undefined behavior. Okay, so that's what we see in the playground. Here, we're passing a reference to the new function, and we assign it to our structure. But here the compiler gets a bit worried about that. He says, yes, you do that, but when you're going to write your code, at some point, you can create a signal variable, assign this reference, we can create this wedge structure, assign this signal variable as a reference, and then drop this signal at some point, and still have your wedge structure that you want to use. And then I will be very confused because I won't have access to the data anymore because you drop it. So I won't compile it. It's something like it's not. I don't have enough information about the relationship between the signal variable and its lifetime, how long it's going to be alive, with respect to Welch to work. I can't. And it makes sense. I mean, it's something, it's very intuitive when you think about it, but it's nice that the compiler do that reasoning for you and warn you about that. Something, again, that C or C++ won't do. Does that make sense, what I'm saying here? So somehow, you need to tell the compiler that what you want is that the signal that you're going to pass as a pointer has to live at least as long as the Welch structure you're going to create exists. Otherwise, you will get into trouble. So it's where they introduce the concept of lifetime. So it's kind of a flag that you need to add to your Welch structure. And with the weird syntax, it's like this. When you have to have flags like this, you can pass to your structure in addition to variable, and they're always in this angle bracket like this. And this kind of weird syntax, the apostrophe with, I put A it's what people use, but you can use D or lifetime or whatever. I use A. What character you use afterward doesn't matter. You can even write full words. But that tells that this is a flag that the compiler is going to track and tell the compiler when the Welch structure you're going to create in your application start to live and when it dies. So it really follows the whole time span, the whole life duration of your structure. And now we have defined this lifetime of your structure, we're going to tag it with the signal. So now signal and Welch share the same lifetime. So the compiler, when we take your code and disassemble it, it will have these two lifetime and it will be able to track them and making sure that one is never dropped before the other. Does that make sense?
Yeah. But so could the signal change and then it would change in the Welch, but the analysis wouldn't?
Yes. Yes.
Okay.
So you still have some work to do to be careful how you do that. But at least you won't have what's called segmentation fault. So a variable which gets out of memory before it's still maybe asked by something else, right? So now I should compile. So you see I have to put the lifetime, declare the lifetime here, and put it here, and here, wherever of my signal reference. Let's see that compile. Undeclared lifetime? Oh, yes, okay, yeah. So if you define the lifetime here in the structure, you need to also not redefine, but redeclare it here in the implementation like that. It's because you can have different implementation and some. Oh yeah, I'm going to explain why they ask you to do that. Why you need to duplicate. Let me check it's compiled first. Yeah, it's compiled now. Because now he's aware, okay, now I know that I have a lifetime for my Welch structure and the signal going to pass has to match this lifetime, otherwise it won't work. So that's very safe. You won't have any segmentation fault at that point. Or you won't compile if you do that at some point. Really illustrate that in a moment. Yeah, so why we need to do that? Because you can have multiple implementation for the same structure, and because, for example, only this one depends of lifetime, you could choose to declare your structure like this if you want to. So you don't really have a need for it, but for that application, no, that doesn't work. I thought it would work. What did I do? I cannot do that. I thought I could do that. Okay, but I'm wrong. I thought, okay, forget what you said. I thought he would accept that. Okay, well, I learned something. Okay, still compile. Okay. So if you go back to, yes?
So
Yeah.
if you made a mistake and you put the lifetime A thing next to the overlap or something, so you're linking it to the wrong variable, would it still run or?
Like that?
Mm-hmm.
No. You apply lifetime to references.
Okay.
Overlap is a scalar, so you see, it won't work. If overlap is also a reference, you can apply the same lifetime. Lifetime is a difficult concept. I want to introduce here, it's relatively easy. Most of the time I will go with a smart pointer. It's another concept that we will introduce later, which are a bit more, which is easier to use. That lifetime, very often when I started with lifetime, and I have to go back and change and either redesign or with smart pointer. But it's a case where it works. In some cases it works fine, and it's one case where it works fine. So it's good to illustrate here how lifetime work and how you can link your references, such as you never lose a variable before you need it. So now if we go back to our example, we can.
If you made a clone of that vector, you wouldn't have to deal with a lifetime.
Exactly. Okay. So sometimes if you have a small vector, we don't bother, you just clone it and that's fine. But if you have a large data, then better use lifetime in that case. So now if we go back to our example, the signal is here. Welsh is defined here, so we're going to pass a signal reference, and now it should allow us to compile and reuse the signal afterwards. The whole thing was just to be able to use it afterwards, the signal. Cargo build / example. Welsh. Yeah, it's compiling. A long time to compile for some reason. But yes, it's compiling here. There's no really problem here. And yeah, and we can use it afterward the signal. We could not before, so that's why. And it's safe. That means if for whatever reason I were doing something like that, I think. Oh yes, if I do that instead, that won't work. Into iter. That's interesting to check that. We have a few minutes left. I try to compile that. It doesn't work again. So it illustrates the concept of lifetime a little bit, because you see I changed iter from iter to into iter. So iter is going to use a reference of the signal to do the sum square. Into iter that uses the value. So you really move the signal into the iterator, consume it, so and at the end you drop it. It's no longer there. So then the concept of lifetime come into play, and the compiler realized, oh, you dropped already. So it says that here. Signal moved due to this method called here into iter, and value borrowed here, and we try to borrow it. So the compiler, because thanks to the lifetime, is aware that the signal has been dropped before you create Welsh. No, you cannot do that. Okay. And even if I put in between the creation and the there we go. Yes, no matter where you put it, it will even if I put afterwards. So the signal now is inside here. So the signal now is the pointer of the signal inside Welsh, and I try to use signal and then drop it, and it's well you cannot do that. you cannot use Welsh anymore because inside Welsh there's a signal that you borrow, and then you borrow the letter. The borrow is later used here. You see what you say? Borrow later used here. So borrow means your signal is used again in Welsh here, so you cannot do that. So that's very powerful.
Why would you use the into iter?
If you it's really depending on your user case. Let's see. If you have a very large vector, for example, and take a lot of memory space, and you are really at the last data processing of that vector, and you don't really want it afterwards, then you put into iter, like this is going to be processed and dropped, and then it will free some memory space, for example, automatically.
Okay.
So this kind of thing. So it depends on your use case, but I use that sometimes when I have large data, and then I am using it, and then toward the end of my functions, I am using the last data processing, I put into an iter like this, dropped.
Mm-hmm. But you can do the same operations with just the iter?
Yes, yeah, okay. The same. So you just, yes and yes. Most of the time, yes, but you see the type of the X, which is the element of X, is a reference when you use iter, and it's a value when you use into iter. Because in some case, iter will take a pointer to signal, and into iter take the value. So most of the time you can do the same thing, but depending on the function you write here, some will ask not to use a reference, but a value or not. So you may have some little modification to do in that case. Okay. So we didn't progress much on the code, but I think it was important to introduce this concept and spend the time to do that. So that's all for, I think, today, the concept of lifetime. Next week, then...
non-intuitive concept. Like, it's really hard to wrap your head around it.
Yes. Oh. It's what Rust is difficult to learn, because it introduces new concepts that we have never been exposed to before. Mutability, ownership, borrowing, etc. It's new. They are very powerful concept because it makes your code much safer. And the code will not compile if you break some of its rules, whereas C or C++ will allow you to do that. But it takes some time to get familiar to it and code according to the rules. So when I started to code in Rust, clone was my friend. I was using it a lot because when I had an error with the compiler, it didn't make sense. I was cloning. And it's fine. And then as you progress, you start to understand this concept more and more, and then you can start to drop clone and then use references, pointer, smart pointer, etc. So that's about it. So next week I will go through generic type. That's another powerful concept of Rust. So we will go through that to improve again our code. All right? Okay, well, thank you very much. Have a nice weekend, and see you next week. Thank you.
Thanks.
Thank you so much.
You too.
Thank you. Bye-bye.
Thank you.